So, good evening, everyone, and welcome to a brand new lecture. We are dealing with electrostatics. This is lecture number 11 in Gauss law, and I think I've lost my specs. Just give me a minute. That's why. Just give me a minute. I'll just come back. Okay, I'm back. Yes, so what I was saying, yeah, we are discussing Gauss law and we had done some really great questions in Gauss law. I was just going through your papers and I saw some more questions. So let me not take any risk and give you a question which is here and which has come in your exam as well. And I'll show you the question that has come in the exam. So this is a question and I want an answer quickly. So let's hope I can get an answer quickly. It's very heartening to see that question of this nature are coming in JEE these days. And I'm talking about JEE Mains now because I just had a look at the JEE Main paper. That was I was doing in the break. And this is the question. A charge Q is placed at a distance of a/2 about the center of a horizontal square surface of edge length A shown in the figure. Find the flux of the electric field through the square surface. And you have 2 minutes to do this and get me an answer. Anyone understands the question? Yes or no? Let's see who gets the answer. Remember, we are doing this chapter only once and we will not get enough time to do it once again before your JEE Main ka first attempt. So this is, we are only doing it once. So we do it once in such a way that we cover each and every aspect. I don't want any question to come from anywhere in the universe that we have not discussed in the class. I'm not taking any chances whatsoever. This one. Yes. What is the answer? Even if you don't do any single question apart from the class, I just want to make sure that we do enough question in the class that is good enough for any exam. How will I do this? Yes? Anyone with an answer? And I wait patiently for an answer. Yes, my dear friends. What is the answer for this one? Again, you'll say, sir, we have not done this question. Any question like this, how can you give that question? We have done this question, trust me. Just have to open your eyes, look at the universe. Trust me, the 4% of what we see is beautiful. Have we done this question? Huh? No, sir. You have not done it, sir. Q by 6 epsilon naught. That is absolutely correct. How did you get the answer? Q by 6 epsilon naught. That is absolutely correct. Well done. How did you get the answer? Q by 6 epsilon naught. This question is same as 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 This question is exactly same as this one, the first question that we did on the cube, where we had placed a charge exactly at the center of the cube. This question is a replica of that question, just asked in a different way. Remember, the edge length of the cube was A, and the distance of charge from the edge will be A by 2, and you had to find out the flux through any one of the faces. So what you do, you put 5 more faces, and now this charge comes at the center of the cube. You are asked to find out the flux through any of the faces of the cube. The answer is Q by 6 epsilon naught. Do we understand this, or this has gone above and saying bye bye? This is the answer to this question. I hope everyone understands it. Yes or no? No, yes. And why did I get this? Because in your previous year JEE Main or Advanced, I don't know from where this question is. Looks like a question from JEE Main. Maybe a question from JEE Advanced. The same thing was asked. And so I thought, why take a chance? This is from 2019. And this is the question that came. A point charge plus 12 microcoulomb is at a distance of 6 centimeter vertically about the center of a square of side 12 centimeter as shown in the figure. The magnitude of electric flux through the square would be, I think this is a question from your integer type, because they are just missing an integer there. I hope we can give the answer for this one. Yes or no? No, yes. Eh?
Yes, sir.
Yes, sir. What is the answer, sir? Okay. Q by 24 epsilon naught. Huh? Q by 6 epsilon naught. Yes or no? We understand this? Yes or no?
Understood, sir.
Understood, sir. Can I move ahead in life? Life has to move on. Huh?
Yes, sir.
Then, sir, this question, sir. Let us see who gives me the answer. This one. Question from previous year. Yes, answer for this one. A charge Q is placed at the one corner of a cube as shown in the figure. The flux of the electrostatic field E through the shaded region is. The more the questions you do, my dear friend, the better you are going to be. And I am not taking any chances. Any chances. And I'm going to show you all the questions that have come, because all of the questions we have done. And that's a good thing. Yes, my dear friends.
Option
Option?
2.
Option 2, Q by 24 epsilon naught. How did you get it? Huh? How did you get it? Q by 24. That is correct. Q by 24. Remember, this is a question of cube at the edge. And they are simply asking you what is the flux through one of the faces. Whatever fancy diagram they have drawn, everything is symmetrical with respect to the charge. Do we understand this? Yes or no? All the faces are symmetrical. Whatever fancy diagram they have drawn, it is basically the flux through one of the edges or one of the faces of the cube. And the answer is Q by 24 epsilon naught. Do we understand this? Yes or no? Huh?
Yes, sir.
Okay, sir. Okay. Then you can see again this question they have asked in JEE, and okay, we have already done this question previously. Also, we have done. So there are some questions that are getting repeated here. This is a question we have done. Okay, again I will show you one question from the previous.
Sir, wait a minute.
Yes, beta, what happened?
Wait a minute, sir. Writing the question.
You don't have to write the question, beta. Don't waste your time in writing the question. Just don't waste your time in writing the question. You will find this question in the previous years. Don't waste your time in writing the question. Have you understood how we have done it? Have you understood that
Sir.
part? Don't waste your time in writing the question. Once you have seen the question, just understand, just draw the diagram. You may not even draw the diagram. You have understood the concept, yes or no?
Yes, sir.
Yes, sir.
That's more than enough. Just look at whether you can do this question or not. Remember this question? We had done a question. I think we have done two questions of this type. Yes or no? In one case, it was colliding with the wall. In second case, there was an infinite sheet place. The same question has come in JEE. Do we understand this?
Sir.
You can do this. Yes or no? Then,
Yes, sir.
then again, from JEE Advanced, this one, an infinite number of point charges are placed. Total force on a point charge. We have done this question, right? Infinite series. Remember that? Yes or no?
Yes, sir.
Infinite series. Okay. Then this one. I think I have given you enough theory about this one. This is just question from your previous years, 2 or 3 years back, and they can really get repeated again. We have done, I've given you full theory on this one, two identical tennis balls and this and that. Yes or no? Huh?
Yes, sir.
We understand this, yes or no?
Yes, sir.
Just feel confident that whatever we have done, and I'm telling you each and every question that I'm seeing, we have done it in the class, each and every question, literally. And I'm not joking and I'm not lying also. If I could share this thing with you, you could see that each and every question that we have discussed in the class is there. This one, see, they have just simply asked the formula. See, charges ka formula they have asked, nothing else. I've given you shortcuts to every damn thing. See this one. Do we remember this disk? Yes or no? 1 minus cos theta. Did I tell you that? Yes or no? Sigma by 2 epsilon naught 1 minus cos theta. Yes or no?
Yes, sir.
See this one. Rod bend like a arc of a circle. I've given you this one. Yes or no?
Sir.
Every question
Sir,
that
option A.
yes, you have done it so many times that that is the power of doing things, doing enough questions that you look at the question and you can tell me, sir, this is the answer. Don't have to do. Let's move ahead. We have done this question. We have done this question. Yes or no? So you must be confident that whatever we have done, it actually covers the entire spectrum that has ever been asked in a JEE or could ever be asked in a JEE. There is not even a single question that I have left for chance. That is why I'm taking a lot of time in covering it. But because I know that there is no more time for you to revise it. See, I had given that question, that cube wala question, na? See, the variation of that question has come. I know what questions are going to come, and there is nothing that we have not covered. You can do this, yes or no?
Yes, sir.
See, the questions are pretty simple. Again, one more from your previous years. See, just have to find where I have to place the third charge so that it does not experience any force. There is nothing. There is nothing that we have not covered that has come in the exam. There is nothing that is left for chance. I have not left anything for chance. Every question in whatever possible form it can come. This is the choose the incorrect statement here. And these are the options. Choose the incorrect statement. Tell me the answer because this is a theoretical question. I will put the incorrect statement here. Yes, tell me the answer for this one. Incorrect statement. Everything I have covered and every word I have said in the class, you will find a question from that word in the examination hall. Which one? Huh? What is the answer for this one? No answers? Just now we have covered this. Huh?
Option 4.
Option 4.
Option 3, sir.
Option 2.
Oh God.
Sir, option 3.
Option 3, sir.
Einstein said two things are infinite. One is definitely the two things seem to be infinite. The universe and human stupidity. And he is not sure about the first one. That means human stupidity is definitely infinite. Universe may not be. Anyways, even after this, if you do something wrong, may God help us. Because I can't do anything better than this. Chalo. On that note, we can move on to the next topic, and the next topic is application of Gauss law. Applications of Gauss law. We have already seen one application of Gauss law in which we had seen that Gauss law can be find out the flux through any closed surface. Remember that? Do we remember it? Gauss law can be used to find out flux through any closed surface. Do we remember this? Yes or no?
Yes, sir.
But again, remember, it can only be used for a closed surface. It cannot be used for an open one. Yes or no? So that is already what we have seen. Now it can be used to find out the electric field due to a very special type of charges which are symmetric. So when I talk about symmetric, 3 or 4 different type of charge distribution, we can find out the Gauss law. We can use the Gauss law to find out the electric field. And what are those different type of charge distribution? It could be a point charge, it could be a spherical charge, it could be a line charge, infinite line charge in fact, and infinite planar charge. So if you have these type of charge distribution, we can use Gauss law to find out, to calculate the electric field because of the symmetry of the diagram. Do we understand this? Yes or no?
Sir.
And out of those, we already know the electric field due to a point charge. How much is the electric field due to a point charge? How much is the electric field due to a point charge? How much is the electric field due to a point charge? We've already done that. We
A Q by R square, sir.
A Q by R square. So how do you find out the electric field due to that point charge? You enclose that point charge in a Gaussian surface. The Gaussian surface that we will use will be a spherical. At all the points on the sphere, the electric field is uniform in magnitude. The angle between electric field and area vector is 0. So integral of E dot dA becomes E into pi r square. Do we understand this? You must know this, right? I'm not going to get into the derivation. I'm just showing you the derivation so that you know how to do it. Total charge enclosed is Q. So now you can apply Gauss law and can find out the electric field. Everyone knows this, yes or no?
Yes, sir.
I'll give you 2 minutes to note it down fast.
The one show previous page.
Previous page?
Yes, sir.
Okay. This is the previous one. Can you move ahead? To the next page?
Sir.
Yes, sir.
This, note it down fast. We have already done this derivation. We know this value. How it is done? We make a spherical surface. Why I'm showing this? Because I might need this to do something else.
Sir.
Everyone done?
No, sir.
Yes, sir.
No, sir.
Do it, do it. Don't worry.
Done, sir.
Everyone done? Okay. Then, point charge, we know the answer. We also know the answer for Q. For non-conducting shell. We know the formula of non-conducting shell. Yes or no? What are the formulas? Now, this is the last chance where you are going to get to again go through the formula of non-conducting shell. Case number 1, when you have the point outside it. So what you are going to do, you are going to create a Gaussian surface which encloses the entire charge. So the answer will be same as the answer of a point charge. Yes or no?
Sir.
This is for a spherical shell. A spherical shell means it only has a charge on the outer surface. It does not have any charge on the inner surface, on the inner side. Inside, there is no charge. So this shell could be conducting or this could be non-conducting. Do we understand this? So for outside points, when you create the Gaussian surface, what you will have, you will enclose the entire charge, yes or no? But for internal points, case number 2, you will not be enclosing any charge. You will not be enclosing any charge, and therefore your answer would be 0. And that is why your field at any inner point would be 0. Everyone understands this?
Yes.
Spherical Gaussian surface? 2 minutes to note it down. Have you noted it down, bacha? This is the electric field due to a conducting or a non-conducting shell. This is also the electric field due to a conducting sphere, because for a conductor, charge cannot come inside the sphere. It comes on the outer surface. Do we understand this? We have repeated these things so many times. Yes or no? Huh?
Yes, sir.
Have you done it, sir? Then one more
Yes, sir.
time, sir.
Yes, sir.
One more time, sir. The graph, sir. The graph of this variation of this electric field. Do we remember this graph, sir? Please note it down, sir. If you don't remember it, I don't know why, but I'm a fan of this graph. It can come anytime, anywhere. Now, we come to a non-conducting sphere. A non-conducting sphere, charges will go inside the sphere as well. Do we understand this?
Sir.
Therefore, we have electric field inside as well as electric field outside. For electric field outside, nothing changes because your Gaussian surface remains same. It encloses the total charge Q, and the answer is Q by 4 pi epsilon naught R square. Do we understand this?
Yes, sir.
So for outside point, nothing changes. The question is exactly similar. But for internal points, what happens is you now have charge enclosed in that. Yeah, you have charge enclosed in that sphere, and therefore you will have to find out how much charge comes inside that sphere. If you have to find out, I hope everyone is taking this. If you have to find out electric field at this point R, you have to find out how much charge comes inside this sphere. And how do you find out? You multiply rho by the volume of the sphere, and that is how you end up with this formula. We had seen the vector form of this formula. Yes or no?
Yes, sir.
That is the difference between internal points and external point. For external point, the total charge Q comes, but for internal point, only how much charge is coming will come. Once again, just to reiterate the fact, I hope everyone is noting this down.
Sir.
This is again the graph between electric field and distance inside the sphere. It is
One
directly
show previous slide.
inside the sphere. It is directly proportional. Then it goes inversely proportional to R square. Okay. I hope so far so good. Huh?
Yes, sir.
Ah. I hope you have noted down case number 1. Yes or no?
Sir.
Case number 2. Note it down, and then I have a question for you. Let's see who can do this. Let me know once you are done, bacha.
None, sir.
Sir.
Then comes this question, sir. Rho means volume charge density inside a sphere of radius capital R varies as rho is equal to rho naught x. Find the electric field inside and outside as a function of x. What is x here? Huh? What is x? What is x? What is x? What is x?
Variable, sir.
What variable? It is the distance from the center of the sphere. So you have to find electric field inside the sphere. If the distance on the sphere is x, center of the sphere. Electric field outside the sphere, if the distance on the center of the sphere is x. Do you understand this? You have 2 minutes to show your talents. Shall I do it? Huh?
Rho r epsilon naught.
Rho r? Where I
4x
mean,
square by 4 epsilon naught.
for which case?
Say, sir.
Inside, sir. Rho x naught by?
Rho x square by 4 epsilon naught.
How did you get it? Yes, I think that might be the answer. I don't know the answer though. How did you get it? How did you get it?
Integrating dq, sir.
Integrating dq. So basically, what you have here is, let me get the diagram from the previous thing. It would be easier for me to it would be easier for me to do the question. So for inside, let me use this diagram. For inside, basically, I have to find it at a distance r or x. So basically, what I need to do is find out how much charge is coming in this sphere of radius x or radius small r. Do we understand this? Now, how I am going to get the charge in this sphere? I will take, and this is how you do it. I will take a, let me take this out. I will take a small shell of radius, let us say small r, and then I will increase the radius by small amount dr. Then I will find out the small charge coming in this small volume. How much is the small charge coming in this small volume? It will be rho, the charge density, charge per unit volume, multiplied by the volume of this shell. What is the volume of this shell? 4 pi r square dr. That is the small charge inside this small volume. Everyone understands this? Yes or no?
Sir.
That's it. So I now put the value of rho. Rho is rho naught into r. So rho into 4 pi r cube dr. That is the small charge dq. Now to find out the total charge, I will have to integrate this from 0 to, let us say, x, where x is the radius, x is the distance where I have to find this. So what will I get here? I will get rho naught. The integral of r cube dr is r to the power 4 by 4. So I will get rho naught into 4 pi into x raised to the power 4 by 4. That will be the integral. That is the charge enclosed. Do we understand this? Yes or no?
Yes, sir.
That is the charge enclosed. I can cancel out this. So this charge enclosed, I have calculated divided by epsilon naught. So divided by epsilon naught, it becomes rho naught into pi into x raised to the power 4 divided by epsilon naught. That must be equal to the flux E multiplied by 4 pi x square, the area of that sphere, 4 pi x squared, 4 pi, pi and pi gone here, 4 will come here, 1 x square cancel. So the remaining thing, the electric field is rho naught x square by 4 epsilon naught. That is the answer for any point inside the sphere. Do we understand this?
Sir.
Now, what will be the difference for any point inside to any point outside? For any point inside, you will integrate it from 0 to x for the charge. For any point outside, what will be the difference? So now, the next question is to find it at any point outside the sphere. How will you get it at any point outside the sphere? This was for inside. Anyone having any doubt, please ask. I just have to find out how much charge comes inside divided by epsilon naught. That will be equal to E into 4 pi x square. I will have to repeat the same steps.
Sir.
Yes, beta.
Rho r cube by 3 epsilon naught r square. X square.
Dimensionally, it looks wrong. Dimensionally,
Rho r cube by 3 epsilon naught x square.
dimensionally, it is wrong. So it cannot be correct. If it is dimensionally wrong, it cannot be correct. So in that case, what I need to do for outside point? Anyone has noted down inside point? Yes or no?
No, sir.
Please note down it for the inside point, and I will move on with the outside point. Again, this question you cannot expect in a JEE main. Probably you will get it in a JEE advanced ka paper.
Done, sir.
Girls, have we done?
Yes, sir.
Okay. Now, how will you do it for any point outside? What is the difference between inside point and outside point? Inside point, we integrated it from 0 to x. We only had to find out how much charge was coming inside that sphere of radius x. But for outside point, what you got to do, you will have to find out the entire charge which is coming in the entire sphere whose radius is r. Do we understand this?
Sir.
So instead of this integral of dq from 0 to x, I will have to find out for outside points, I will have to find out the charge, and I will integrate it from 0 to capital R, not x. So the answer for that one will be, just replace x by r and you get your answer. So it will be pi, it will be integral of rho naught 4 pi small r cube dr, but the integral is set up from 0 to capital R. So the answer in the first case you are getting rho naught pi x raised to the power 4. Here you will get rho naught pi r raised to the power 4. Do we understand this, bacha? That is the first difference. Do we understand this?
Yes, sir.
But on the left hand side, your E multiplied by the surface area still comes for the entire sphere of radius x. So on the left hand side, I will have E multiplied by 4 pi x square. But on the right side, I have rho naught pi r raised to the power 4 divided by epsilon naught. That is the difference between inside and outside. For inside, I integrate it from 0 to x. For outside, I cannot integrate it from 0 to x because charge is not coming from 0 to x. Charge is only coming from 0 to capital R. Do we understand this?
Yes, sir.
That is the answer for electric field outside, my dear friends. Pi and pi will get cancelled. Terms are like that. Just a small change. Electric field now becomes rho naught r raised to the power 4 by pi small r square into epsilon naught. Do we understand this? Yes?
Yes, sir.
Or no?
Understood, sir.
Okay. Well done. I'll give you a minute to note this down. Let me know once you are done.
Done, sir.
Boys?
No, sir.
No, sir? Let me know if you are done, so that I can move ahead in life. Life has to move on. We cannot be stagnant in life. So I have given you this one
Done,
variation.
sir.
They could vary rho in different ways. I had given it rho naught into x. They can vary it as rho naught divided by x. They can vary it as rho naught into root over x. Doesn't matter. I can make infinite number of variations. The process remains same. And the process is very simple. And what is the process? You just have to find out electric field. To find out electric field inside, you have to find out how much charge is coming in the sphere inside. To find the electric field outside, you just have to find out how much is the total charge in the entire sphere. Do we understand this, everyone? You have understood the difference, yes or no? Because it's not possible for me to make all the variations because it is all mathematics, nothing else, how rho varies. So I've just showed you one variation, and the rest of the variations, even if they come, they are purely a question of math. Shall I move on in life?
Yes, sir.
Okay, now we take the next step and we move on and we find out the electric field due to an infinite long charge. And we already know the answer for an infinite long charge. We will just see how this is done so that the next question or the next to next question we can do using what we have done here. Now, I've got this beautiful diagram for you so that I don't have to draw my stupid ones. This one. Gaussian surface is cylindrical in shape, as you can see. And what we have here is an infinite line charge. Ding, 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 ding. It goes away like this. Now, I make a cylindrical Gaussian surface. Why I make a cylindrical Gaussian surface? Because at all the points on this curved part, the electric field would be constant in magnitude. Do we understand this? Because of the symmetry of the diagram, yes or no?
Yes, sir.
And again, this will remind you of that thing that we had done, line charge, cylindrical. Does it remind you of anything? Line charge, cylindrical. Anything? Huh? Line, cylinder, point, sphere, anything? Nothing. Gajni only looks good in a cinema hall. Is a useless fellow on in daily life because he'll forget what he was doing 5 minutes before. Huh?
Wave optics.
Wavefront. And this is cylindrical surface. This is actually an equipotential surface. All points are on the same potential. We'll come to that. Okay, so I have got a cylindrical thing. Electric field will go always perpendicular to this, and this area vector, closed surface area vector, always goes perpendicular to it. So the angle between E and DA, how much is the angle between E and DA? See, they are also colorful people. They use all sorts of fancy colors. I like colors. So you see the electric field E and DA. What is the angle between electric field E and DA? It's 0. And that is why you can only find out electric field in very special cases, because you need a special case where electric field and area vector are also in the same direction. So angle between electric field and area vector is 0. So if you find out the flux through this entire cylinder with the two caps, it will have a curved part, which is the blue part, the curved part. Then you have two caps. Do you see the two caps, upper surface and the lower surface?
Yes, sir.
This is the upper surface, ding, 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 ding. And this is the lower surface. Ping, 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 ping. Now, here the scenario is different. Electric field lines are going like this. And area vector for the upper surface is like this. And for the lower surface, it's like this. So for both these surfaces, your flux becomes 0. Do we understand this?
Yes, sir.
For this one, as well as this one, the flux becomes 0. So the only flux is through the curved part E into dA. The total charge enclosed is lambda multiplied by L. Lambda is the charge per unit length multiplied by the length of the cylinder, will be the charge enclosed in the cylinder. E into 2 pi RL becomes lambda L by epsilon naught, and we get this beautiful result, lambda by 2 pi epsilon naught R. is the electric field due to this type of charge distribution. I've also told you to remember the vector form of this. What is the vector form of this? How will I write this in the vector form? Huh? How will I write this in the vector form, bacha? I don't know. What about vectors? Forget vectors. How will I write this in the vector form?
Lambda r vector by 2 epsilon naught r square.
So here you can simply multiply it by r hat, or you can multiply it by r vector and divide it by the magnitude of r vector. So lambda r vector divided by 2 pi epsilon naught r square. Everyone got this? How I got this infinite wire? Huh?
Yes, sir.
Noted this down, everyone, so that I can move ahead with life. Huh?
Sir.
Girls, we are done.
No, sir.
Okay, now boys are ahead. Good. Healthy competition. Girls versus boys. Let me know once you're done so that I can move ahead in life. Life has to move on. Boys, are you noting it down? Yes or no? I see some of them doing exercise and some of them chilling out.
Answer.
Answer.
No, sir.
See, I have an all-seeing eye. I can see everything that's happening. Even
Sir.
you might miss something, but my all-seeing eye does not miss anything. Next one is an infinite cheat. Infinite cheat. Now create a Gaussian dabba. Gaussian pillbox, we call it. This type of Ala cylinder is known as Gaussian pillbox. Pill. And medicine pill. Gaussian pillbox. So in this Gaussian pillbox, I have one curve, one circular part here, one circular part here, and then we have this curved path. And here, ulta thing happens. The flux to the curved part is 0 because electric field lines go like this, and the curved part ka area vector go like this. So this flux becomes 0, and only flux is through the circular part, and therefore the answer is sigma by 2 epsilon naught. Do we understand this? How it is done? Or shall I explain it more? Huh?
Understood, sir.
This is the front part, this one. And this is the rear surface, which we cannot see because this is a 3-dimensional diagram. So this is somewhere here, right? The flux through this curved part is this blue gentleman. This blue gentleman now becomes 0 because my electric field lines are going like this, and your area vector is going like this. That is the faida of drawing a diagram so that I can do the jig and move forward. So the flux through this curved part is 0, and the flux through this two circular part becomes 2E into S, where S is the area of this curved part. No, not curved part, the circular part. And how much charge is coming? How much charge is coming in that much of area? That same charge is coming here. Ding, 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 ding. Do you understand this? So the charge is sigma into S divided by epsilon naught is equal to 2 times E into S. Ding, 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 ding. Things get cancelled. And this is the only type of charge distribution which produces uniform electric field. An infinite sheet produces uniform electric field. Do we understand this, or this has gone above what I'm saying? Bye bye. Bye bye. Bye bye. Bye bye. Huh?
Understood, sir.
Understood, sir. You have 2 minutes to do whatever you are doing. Note it down, sir. अच्छा, shall we move on in life, or your life has become stagnant? Huh?
Wait for 1 minute, sir.
What, bacha?
Wait for 1 minute.
Wait for 1 minute. I shall wait. Don't worry. Time is a luxury that we have right now because we are, I think, doing okay with the time that we have got. Yes, bacha. Shall we? Huh?
Sir.
And this is a question taken from your favorite book, S.C. Verma. And this is the question that that I gave you, that hole inside that cylinder, and this it comes from here. A long cylindrical volume contains a uniformly distributed charge of density rho. So I hope you can see that. Find the electric field at a point P inside. They have asked you to find out the electric field inside, but I will ask you to find the electric field everywhere.
Rho r by 2 epsilon naught.
Everywhere you have to find out the field. Everywhere, when I say it has to be on the axis, it has to be inside, it has to be on the surface.
Rho r by 2 epsilon naught, sir.
It has to be outside as well. Everywhere. So get the answer for everywhere. To find out everywhere, you must know the radius of this cylindrical surface, and the radius of this cylindrical surface is r. I have the answer for inside. What about the answer for outside? So let us give everyone some time to take a deep breath. Take a deep breath.
Rho r square by 2 epsilon naught x.
Rho r square by 2 epsilon naught x. That is correct. Good. That is correct. Well done. What about the others? What is the electric field on the surface? On the surface, beta. And remember the graph. And remember the vector form.
Rho r by 2 epsilon naught.
Rho r by 2 epsilon. Where is the electric field maximum?
On the surface, sir.
Very good. Well done. What about the others? Okay, tell me, how are we supposed to do this? Remember, it's a cylindrical volume. So the only way you can make a Gaussian surface will be in the form of a cylinder. We understand this, everyone? Yes or no?
Sir.
Okay, so I make a Gaussian surface in the form of a cylinder here. So the cylinder will go like this: ding 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 and ding 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 ding. Now electric field at all the points on the curved surface will be same. On the circular part, it will not be same, but that flux is 0, so I don't have to worry. I don't have to worry about the circular part because the circular part flux will be 0. Do we understand this? Yes or no? Everyone understands this? Yes or no?
Yes, sir.
I
Sir.
just have to find out how much flux is going through the curved path. And how much flux is going through the curved path? Electric field and area vector are coming in the same direction, so the angle is 0. So I just have to multiply E with 2 pi XL. That will be the flux through the curved path. So what is the flux through the curved path? The flux through the sphere is E into 2 pi XL. That is the flux. And this flux must be equal to how much charge is coming inside this. How much charge is coming inside this? That will be equal to is charge density rho multiplied by the volume of this thing. What is the volume of this thing? It is pi x square into L. The volume of this cylinder, ding 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 ding, divided by epsilon naught. And here you are with a beautiful answer for this one. Pi getting cancelled, this getting cancelled, L and L getting cancelled. The electric field is a very nice rho x by 2 epsilon naught for any point inside the cylindrical volume. If you want to find out the electric field on the axis, you just put x as 0 and electric field on the axis becomes 0. This is the electric field at any point inside. Do we understand this? Yes or no? No, yes. Huh?
Sir.
Everyone understand this?
Yes, sir.
Now, has everyone noted it down? Yes or no?
Done, sir.
And how I am going to find it out for outside points? I will repeat the same step. I will do it in blue now. So now my cylinder looks like this. Now this is my cylinder that I have created. This is the cylinder that I have created. The radius of the cylinder still remains x. Now again, the flux through the circular part is going to be 0. I don't have to worry about it. I only have to see the flux through the curved part. And now to find out the flux through the curved part, again, E and area vector are going in the same direction. So the flux through the curved part is E into 2 pi XL. It does not change. Do we understand this? Yes or no? That must be equal to the charge enclosed in this cylinder that I have created. Now to find out the charge enclosed in this cylinder, you must understand that only charge coming in this much portion, which is inside the cylindrical space, will be considered. So how much is the charge coming in this pink surface? The charge coming in this pink surface will be rho into pi r square into L, the volume of this cylinder, divided by epsilon naught. We do L, say L will get cancelled, pi, say pi will get cancelled, and you will get phi as, oh sorry, not phi, you will get your electric field as rho r square by 2 epsilon naught. This is for points which are outside the cylindrical space. If you have to find out the electric field on the surface, the electric field on the surface can be found out from inside or outside. Just put x as r and you get the answer for the surface. Electric field on the surface is rho r by 2 epsilon naught. One more thing that you have to understand is the graph of your electric field with R, and you may have a question on this. How does the graph of electric field with R look like? It just goes like this. Inside the cylindrical space, it is directly proportional to x. Do we see this? Yes or no? And then outside, I have missed x here. And outside, it is inversely proportional to x. So the graph is like this, and the electric field is maximum on the surface, and the value is rho r by 2 epsilon naught. You can compare this diagram, you can compare this field with the field created by a non-conducting sphere, and you will find uncanny resemblance. The only resemblance, the only difference is here it is rho r by 2 epsilon naught. There it was rho r by 3 epsilon naught. So there is only a difference of 2 and 3. Do we understand this? Yes or no?
Yes, sir.
Everyone understands this? Yes or no?
Yes, sir.
Now, using this formula, you could have calculated the question of this cylinder with a spherical hole. Moving ahead, we can also write this electric fields in the vector form, because then you can devise a question based on this. So this electric field, if it is written in the vector form, this electric field inside will become rho x vector divided by 2 epsilon naught. Do we understand this? Yes or no?
Yes, sir.
For this outside points, it becomes, can anyone tell me the vector form for these outside points? Rho r square x vector by 2 epsilon naught x square. You can write it in this fashion. Do we understand this, or this has gone above our head saying bye-bye?
Understood, sir.
Bye-bye, sir. Going.
Understood.
Okay. Anyone has noted this down?
Yes, sir.
Yes or no?
Done, sir.
Shall we move ahead?
Yes, sir.
Sir.
I'm looking for a question. Okay. Oops, what has happened? Sometimes strange things happen. Just give me a minute. My laptop has got confused with all the time traveling that I was doing. It has got bamboozled. Now just trying to regain some senses. Because I've been doing a lot of time traveling. I was going back in the past to get a question from there, and this thing got bamboozled. How far I've gone back in time. To go back in time, now I'm back. I'm back to the present stuff. Okay. So once we have done this, then we can remind ourselves of this one. And I hope you remember this question. This was a diagram that I had to fetch from the past. And you remember this question that we had done. This was a sphere with a spherical hole, and we had found out that the electric field at any point inside that hole is constant. Do we remember this?
Yes, sir.
Everyone understand this? And we had also found out that it only depends on the position of this. So if I have to find out electric field at point A, it will be rho r vector by 3 epsilon naught. Do we remember this? Everyone remembers this question?
Yes, sir.
Sir.
The same question could be made for a cylinder. So instead of this being a sphere, it could be a cylinder. A cylinder with a cylindrical hole. Do we understand this? And this is the top view of that cylinder with the cylindrical hole. Anyone understand what I'm talking? Cylinder with a cylindrical hole. Do we understand this? Huh? Are they say yes or no?
Sir.
So again, remember, if this question is cylinder with a cylindrical hole, what is the electric field at point A or any point inside that hole? It will be constant. And what is the value for a cylinder with a cylindrical hole? This red one is the value for sphere with a spherical hole. For cylinder with a cylindrical hole, what is the answer? Huh? For cylinder with a cylindrical hole, what is the answer? No one knows the answer. For cylinder with a cylindrical hole, the answer becomes rho r by 2 epsilon naught. So remember, whatever question we had done for sphere with the spherical hole, we had given a lot of time to find out the answer for sphere with a spherical hole. Do we remember this? Yes or no? The same question can be done for cylinder with a cylindrical hole. The only difference will come in this if you write the answer in terms of rho. The only difference between those two questions is wherever there are 3 comes, here 2 will come. So the same thing can be repeated for cylinder with a cylindrical hole. Everyone understands this? Yes or no?
Yes, sir.
Then that takes us to the last problem of this Gauss law. And again, this is a problem from your favorite book, SCV. The next problem after the cylinder, and that is the next problem here. Now we have a non-conducting sheet of very large surface area and thickness d, and it contains uniform charge whose density is rho. Find the electric field at any point P inside. They're asking any plate inside. I can add inside, outside, surface, axis, everywhere. What is the electric field at a point P as a function of x from the central plane? Draw a qualitative graph of E against x. That is the last question for your Gauss law, because we have done everything that was possible. How to do this? Huh? Any idea, anyone? Well, I will give this question as a homework. So, you can take this question as an homework. Try it at home. The answer everyone knows, rho x by epsilon naught. The answer is known, but how do you get it? And remember that answer. And remember that answer, this is answer for inside. You have to remember the answer on the surface, and you also need to remember the answer for any point outside, because you never know what can come in a JEE. The concept remains same. The questions might be a bit different. So I take your leave today, and we have done so-called Gauss law. We are done with all types of variations. Everything that is possible has been covered. This is the last question. We'll do it in the next class, and we will move ahead with the next topic, electrostatic potential energy. We'll deal with that topic in the next class. Take care. God bless all of you. Bye-bye. Any doubts? Always there. See ya.